Okay, so in this lecture what I'm going to do is take you through the material that's presented in lecture 7. So obviously I'll do this in class, but it is quite a complicated lecture. There's quite a lot to think about, and as we go through the lecture, which has been carefully prepared, it's, I guess, in class quite easy to lose track and not be able to follow the animation. So I guess what we'll do is we'll work our way through this lecture, and I'll I guess repeat what I would be doing in the classroom, but you have, at least with this video, the opportunity then to pause, rewind and reconsider the lecture as it's presented to you. So as you know, the object of the lecture is to basically show you how a simple program can be executed. So at the very beginning of the lecture we spend a little bit of time talking about the various components of the computer. So we talk, for example, about the data path, the flow of data and instructions around the data path, the role of the control unit in terms of the work that it carries out, controlling the fetching and decoding and executing of machine code instructions. And we also are very mindful of the reading and writing of data and instructions between the CPU and the primary memory. So all of those things, I guess, are discussed at length in lecture number 6, which is about the components of the CPU and the primary memory. So I won't recap them here, but instead what I'll do is I'll move very quickly on to a simple example program. So you'll recall from the class that what we do is we start out with something that we might see in an ordinary program written in a programming language like Java. So for example, we might see something like C equals A plus B. Now you know from your studies in Java that A and B, they're variables and they contain integer values, and you know that if you see A and B written down in a program, then actually what's being referred to is the value of the variable rather than the actual letter A or the letter B itself. So if A, for example, has the value 10 and B has the value 13, then you know that they're going to be added together, and that the consequently then that value of 10 plus 13, 23, will be assigned into the variable C. You also know that that line of code can't be executed directly by the computer system. It has to be converted into a lower level format, and you know that the way that that's done is through the process of compilation. So one of the things that we can say about C equals A plus B, and we can say this from the perspective of thinking about it at the lower level of how the computer operates, is that each of these variables, A and B and C, well, they have to be stored somewhere in the computer system, and the only place where they can be stored is inside the main memory. And in fact, given what we know about main memory, that it's composed of an array of cells, it seems logical that each variable, the value of each variable, would be stored in a particular cell in main memory. So we might assert that A is stored in memory address 101, we might assert that B is stored in memory address 102, and we might assert that C is stored in memory address 100. Now, what we could also assert is that C equals A plus B could also be translated, or is translated, into a number of lower level instructions which the CPU executes directly. Now, for the sake of clarity, we won't really talk about these instructions in terms of their specific implementation. We'll just say what they do. So instruction number 1 would be to read the value of A from primary memory cell with the address 101 into the CPU. Instruction 2 would be to get the value of B and bring that from its memory address 102, cell 102, into the CPU, and then to add A and B together and store the sum of the two values temporarily in the CPU. And then instruction number 3 would be to do the assignment, which would be to take the sum, the result of the addition of A and B, and assign that out to the cell which is associated with the variable C, and that would be the memory cell with the address 100. Now, there's a couple of key points here. These three low-level instructions, they are what we would call machine code instructions. We need three of them in order to execute the higher level C equals A plus B. And each machine code instruction is, if you like, a unit of work for the CPU, in that the CPU must fetch the machine code instruction, decode the instruction, and then execute it. So although we see something at the high level C equals A plus B, in actual fact, when we consider it, and we can illustrate this with a diagram, C equals A plus B is in fact equal to three instructions that have to be directly fetched, decoded and executed by the CPU, and each of those instructions requires requires in turn to be fetched, decoded and executed. So C equals A plus B translates into 9 separate things that the CPU must do in order to execute the 3 machine code instructions which are equivalent to C equals A plus B. So that's our kind of overview, if you like, which is pretty straightforward. High-level instructions get converted into low-level machine code instructions, and each of those low-level machine code instructions has to be fetched, decoded and executed by the CPU. Now, as we proceed into the lecture, we can see that we have an extension of what we've been talking about up to this point. And you can see that on slide 16 we've got a program which I guess is pretty straightforward. We can see that it consists of 5 lines of code. You can see that there are 3 variables, A, B and C, and that initially A takes the value 10, B takes the value 13, C takes the value 0, and then on line 4 you can see that A and B are added together and that the result of that sum is assigned into the variable C. So C would start off with the value of 0, but then once line 4 had been executed it would contain the value 23. And then on line number 6 you can see that we have a pseudocode type print statement which takes the value of C and prints it out to the terminal or out to the screen. Now we know that this can't be executed directly by the computer system, by the hardware of the computer, and that it has to be translated into a lower level form which can be executed directly by the computer. And we know that this form is a binary form because that's the only language that the computer actually understands, and the usual process by which this is done is through converting the high level form of the program into the low level form of the program by using a process of compilation. So that's what's illustrated in the next couple of slides. You can see that we have the symbolic version of the program that we've just been looking at. It won't make much sense to you, and the reason why it won't make much sense is that we have written it using the symbolic form of the machine code instructions that directly get executed. We don't write them in binary directly because if we did we wouldn't be able to understand them. Remember that one of the teaching points that we made in a previous lecture is that binary is pretty unintelligible to just about everybody, and therefore we use things like hexadecimal, or in this case we use just words that, although we're not necessarily familiar with their meaning, we can read them. So we can see that, for example, you've got a first machine code instruction in its assembly form which reads loco 10, the second one reads stod, store direct 101, and then loco 13, and then stod 102, and loco 0, and then stod 100, and then lodd 101, and then add 102, and then stod 100, and then lodd 100, and then out. Now we don't know what any of these mean. We might be willing to hazard a guess that add with the 3 Ds, that it has something to do with addition, but the rest of them, they're not going to be obvious to us. So what happens is that the programmer writes the program using the high-level programming instructions like Java, and then the compiler, the bit of software that converts them into the low-level symbolic instructions, and then oversees the translation of those symbolic assembly instructions into low-level binary machine code instructions, which can be directly fetched and executed by the CPU. So that's quite easily illustrated in the next slide. So you can see there's our programmer, and they write the simple program that we've been looking at in something like JGrasp. They press the button on the JGrasp toolbar, and that converts the high-level format into its lower-level assembly form, and then that in turn is converted into its binary executable form. So it's the low-level binary executable form that's fetched, decoded, and executed by the CPU. But primarily when we talk about machine programs, when we talk about machine code instructions, I'll use this format here, which is a symbolic format where each machine code instruction or each assembly instruction maps to a binary form over here. So loco 10, when it's translated into the binary form, becomes 0111 0000 0000 1010. And likewise, all of these instructions here, all 11 of these instructions, they have a binary equivalent, which is shown here. So the task that we have to do is, I guess, twofold. We have to figure out what these machine code instructions actually do, and then we would like to visualize the fetching, decoding, and executing of these instructions. We'd like to gain an insight into how the CPU actually executes this program. Okay, so that's the objective that we're seeking to obtain here, and that's what we'll proceed to look at in a minute. Okay, so slide 20 contains a table which gives us some additional information about these instructions. So you can see that we have presented here in the first column the memory address. So the memory address is just the cell in main memory where each instruction is stored. So the idea is pretty simple. As we execute our program, we will fetch, decode, and execute each machine code instruction in turn. So for example, we'll start off with loco 10, and then we'll execute stod 101, and then we'll have loco 13, and so on and so forth until we have gone through all 11 instructions. So the first column just shows you the addresses in memory where they're stored. I've given them here in binary, but when we actually get to the figure, the animated figure, you'll see that I'll give them to you in decimal and hexadecimal, and that will be certainly much easier to understand than their binary forms that are presented here. You can see also that we look at machine code instructions in two components. They have two parts to them. One is the operator, and then the other part is known as the operand. So if I was to tell you that our first instruction is loco 10, well then we would say that the operator part is loco, and we would say that the assembly part is, that the operand part is 10. Now remind yourself that when we look at the assembly form of a machine code instruction, that's symbolic so that human beings can understand it, but what the actual computer sees is a 16-bit number. And we can break that 16-bit number into two components, and we can say, okay, the first 4 bits represent the operator part of the machine code instruction, and the remaining 12 bits represent the operand value. Now you can see that our instruction is loco 10, so the first 4 bits are 0111, and that's the binary representation of the operator part of this instruction. And then if we look at the remaining 12 bits, you can see that the final 4 digits are 1010, which of course is the binary representation for the decimal value 10. Okay, now if we look at some of the other machine code instructions, for example stod 101, which is an operator of stod and has an operand value of 101, and then we look at the 16-bit binary number that represents that instruction. We can see that the first 4 bits are for the operator. So 0001 tells the control unit of the CPU that what we're dealing with is a stod machine code instruction. And then if we examine the remaining 12 bits, and I'm not going to do this manually, but you can take it from me, that binary number there, that 12-bit binary number that I'm highlighting at the moment, that represents, when it's translated into decimal, the binary representation of 101, decimal 101. And so it proceeds. You can see that each machine code instruction has an operator and an operand. The first 4 bits of each machine code instruction, when we look at them in their binary form, tell the control unit of the CPU what machine code instruction is to be executed, and then the remaining 12 bits are the operand. They're the thing that suffers the result, the consequence of the execution of the operator. The 5th column, is it the 5th? And the 6th column is a column reserved for what's known as the register transfer notation. Now, we're not going to pay too much attention to this at the moment, but it is a very useful column for us to be mindful of, because what it does is it tells us what the consequence of the or the effect of the instruction will be when it has been executed. So if we execute, or if the computer or the CPU executes the machine code instruction loco 10, when that instruction has been fetched, decoded and executed, well, the register transfer notation says that what will have happened as a consequence of the fetching, decoding and executing of that particular instruction is that C, which is a constant value, will have been put into the accumulator register inside the CPU. And likewise, when we've executed stod 101, well, I can see that by looking at the register transfer notation that the overall effect of stod 101 is that whatever values in the accumulator will have been copied to the address X in main memory. So all of these register transfer notations, they're quite useful, because when we go to do our own assembly programming, one of the things that we'll have to do is to actually choose the right sequence of machine code instructions to actually program the system so that it works effectively. Okay, and then the final column is just telling us a little bit about what each group of machine code instructions does. So I can see that the first 6 machine code instructions inside this program, they initialize the variables. Instructions 7 and 8 add A and B together. Instruction 9 assigns the result of the addition of A and B to the variable C, and then the last 2 instructions, they're responsible for taking the value of C and printing it out to the terminal. So the terminal is just a screen on which we can print data from our simple computer. So all of that's explained in slides 21, 22, and what we'll do in a minute is we'll look at the actual animated presentation part of the lecture, and we'll look at the behavior of this computer as it executes these machine code instructions. But on slide 23, you'll also see a table which specifies the available machine code instructions for this simple computer. Now, real computers have hundreds of machine code instructions, but our computer only has about, how many is it? 15, I think that is, or it's not even 15. It's a very limited number of machine code instructions. So you can see that our table specifies the binary representation. So there, for example, is loco, and you can see that the first 4 bits are just the same as we looked at previously, 0, 1, 1, 1. You can see that it has a symbolic form, which is loco C, and then there's a column that tells us something about what it does. So load constant means that this machine code instruction loads a constant value into the accumulator of the CPU. And then if we look at the actions column, you can see that C goes into accumulator, where C is a value that is between equal to or greater than 0 and less than or equal to 4095. And if you stop and reflect about that for a second, you'll remember that if you have 12 bits, then the range of numbers that you can represent with those 12 bits is 2 to the power 12 minus 1, which is, of course, 4095. Okay, now when I'm doing this in class, will actually give you a printout of slide 23 to keep in front of you. It's quite important because it's your aide memoir for what is being done with the computer for the actual machine code instructions. So we'll see that table again and again, but for the moment I'm going to just pause, and you should remind yourself that if you're doing this at home off your own bat, then you need to have the presentation full screen in your PDF viewer so that you can really get the appropriate and full detail of the animations as we proceed through them. Okay, so you can see that on slide 25 we make some points about the way that the presentation is structured. So I'll actually skip past these, slide 25 and slide 26, but I think that if you are doing this for the first time, you should take a bit of time to read slide 25 and 26, and although I'm just about to refer to them in a little bit of detail as we go through the presentation, it's important that in particular you're able to remember what the different registers do. So each register inside the data path of the CPU has a fairly specialized function, and I'll draw your attention to them as we go through them, as we go through the animation, but I'm not going to reread the slides here, and I would say to you that what you need to do is to look at these later and try to memorize them, or at least memorize them as best you possibly can, so that you can say, okay, instruction register, IR stands for instruction register, and the purpose of that register is to store the machine code instruction while it's being decoded and executed. But we'll see more of that in due course, and what I'm going to do first of all is I'm just going to start immediately into the animation. So you'll recognize that the structure of the remaining part of the lecture is broken into sections, and each section details the fetching, decoding and executing of a machine code instruction. So remember that the program that we're looking at is the one where we have A equal to 10, B equal to 13, C equal to 0, and we add A and B together and we end up with 23 being assigned to C and then printed out. So our first instruction that we'll be looking at is loco 10, load constant 10. Okay, now you can see that on slide 28 we detail exactly what is done by the control unit in terms of the actions that it needs to carry out in order to fetch the machine code instruction loco 10 from the main memory. Now, although this looks like quite a bit of work, it is actually highly structured, and it essentially works like this, and it's the same for every instruction when it is fetched. So step 1 is we load the contents of the PC register into the memory address register. So the memory address register will now hold the value of the address that is to be fetched. This control unit then asserts a read, and that causes the main memory to take the contents of memory cell 50 and put it on the data lines of the memory bus. And then step 3, instruct the MBR to read the data bus, and step 4, transfer the contents of the instruction register into the transfer the contents of the MBR into the instruction register. So the instruction register will now contain the instruction loco 10. And then finally increment the PC register so that it points to the address of the next machine code instruction. So PC will now take the value of PC plus 1. So all of that seems quite overblown, but actually when we see it illustrated, it's not so bad. So the first slide that we look at is just showing us the structure of our computer before really we do anything that is of significance. So on the left hand side you can see our main memory. You can see that we have individual cells. Each cell contains an instruction, and you can see that the instructions start at cell 0. Remember that each cell has an address, which is a unique number that's used to identify the cell that the CPU wants to interact with. And then you can see that we have a set of machine code instructions presented in their symbolic form. So you can see that the first of the instructions is stored in cell 50, the second in cell 51, 52, 53, 54, 55, 56, and so on, all the way through to the last instruction, which is out, and that's stored in memory address 61. Now, just before we go to execute our first instruction belonging to the program, we can see that the state of the computer is that it has been executing previously unknown and unspecified machine code instructions. So we can see that inside the instruction register there is a machine code instruction, the details of which we haven't specified. Inside the accumulator register there is some value from a previous computation. We can see that the PC register, the program counter register, contains the value 49, so that would be the machine code instruction which was stored at address 49. And then we can see that the MAR registers contain an address value, and the MBR register contains a value. Now all of this is not germane to anything. It's really just showing you that the system was doing something before it starts to execute our program. So when we move on to the next slide, and you can see that each diagram has an identifying label. So you can see that we started off with CPU 1A, and then we're on CPU 1B, and then we move on to CPU 1C. So what we're doing is we're beginning the execution of our simple program, and what we're going to do first of all is initialize the variable a with the value 10. But before we do any of that, the first thing that has to be done is we have to fetch the machine code instruction that's going to be decoded and executed and bring it into main memory. So you can see that the machine code instruction that we've presented that we're going to focus on is called loco 10, load constant 10. So the first thing that the control unit of the CPU has to do is to use the value that's in the PC register, the program counter register, and assert that into the memory address register. So basically what we're doing is we're going to have the CPU instruct the main memory to give us the contents of memory cell 50. Once that's done, and you can see that that's highlighted in the actual diagram with a red highlighter that shows you the value 50 being copied from the PC register to the MAR register, we then go to the next step, step 2, which is to read from main memory. And you can see that down here the control unit of the CPU sends a read signal to the circuitry of the main memory, and the circuitry of the main memory says, okay, I have to provide the contents of cell address 50. The operation that I've been instructed to carry out by the control unit of the CPU is a read operation, and that's exactly what the circuitry does. It obeys the instruction that's given to it by the CPU, and you can see that the contents of cell 50, which contains the machine code instruction loco 10, that is then copied over the memory bus and asserted as an input to the CPU. So step 3 is to copy the contents of cell 50 from the memory bus and bring it in to the MBR. Now remember that the function of the memory buffer register is to just act as a temporary holding area as data goes from the CPU to main memory, or as it goes from main memory to the CPU. So in this case, because we're doing a read, the value that we're copying is going into the CPU, so it goes from the memory bus into the memory buffer register. Now the memory buffer register doesn't really do anything apart from hold the instructions and data that have come from main memory temporarily. So that then brings us to step 4, which is that the value that's in the memory buffer register gets copied up into the instruction register. So you can see that the path that is taken by the binary bit pattern that represents loco 10, that is somewhat awkward. So you can see that it has to travel through the ALU. Note that it just passes through the ALU without being changed, and then it comes out of the bottom of the ALU, and then it travels up via the C bus until it gains entry to the scratch pad registers. So now the machine code instruction is inside the instruction register, which is the proper place for it to reside. That's where it will then be decoded in the next part of this machine code instruction. But we're not quite finished the fetch yet. We have to increment the PC register by 1 so that it now goes from 50 to 51. Now, why would we want to do that? Why would we want to increment the PC register by 51? Well, remember that this program that we're looking at, which consists of 11 machine code instructions, well, remember that we have to work our way through all 11 machine code instructions, and we have to fetch, decode, and execute each of those 11 machine code instructions in turn. And we won't be able to keep track of those machine code instructions by some magic process. The CPU has to have an address which will tell it where the next machine code instruction in the sequence that's going to be executed is located. So all we're doing is incrementing the PC register so that when we go to the next machine code instruction, the CPU will say to itself, okay, where's the next machine code instruction? It will look at the PC register and it will see 51, and then that's where it will go to get the next machine code instruction. It'll go to cell 51. So that concludes the fetching of the machine code instruction loco 10 from the main memory into the instruction register. And you can see that the CPU had to do 5 discrete separate operations in order to do that very, very simple thing, which is just bringing a machine code instruction into the CPU. And remember that at this point it hasn't decoded it and it hasn't executed it yet. So that's the next part of the cycle. So I lump the decoding and the executing of loco 10 into one part, one animation. So what does loco 10 do? Well, if you consult your table, you'll see that loco is an abbreviation for load constant, and if you look at the RTN specification of that machine code instruction, you'll see that what it does is it loads a constant value into the accumulator. So what is the constant value? Well, it is 10. Now remember that the first line of our program was A is equal to 10. So the value 10 is the constant value that we want to assign to a variable. So what load constant 10 does, loco 10 does, is it takes the value 10 and it puts it into the accumulator. Okay, so you can see that there are 3 steps to that. I won't read these out, I'll just go to the animation, and you can see that the control unit takes the operand part of the instruction. So remember that machine code instructions have 2 parts to them. The first is the operator, which in this case is loco, and the second part is the operand. So the operand is 10, which is the constant value, and you can see that that travels on the B bus to the ALU and becomes an input to the ALU, and then in the next frame in the animation that 10 travels through the ALU without being changed and travels back via the C bus to become an input to the scratch pad registers. And then finally you can see that the value 10 is copied in to the accumulator. So that's the decoding and executing of one machine code instruction. So that's 1 out of the 11, and you can see that if we're thinking about it in terms of, you know, A equals 10, well then all we have really done is bring the value 10 into the accumulator. And in order to do that in our very, very simple animated computer, that took 8 separate discrete operations to implement the fetching and decoding of that machine code instruction, loco 10. So we'll review now the fetching, decoding and executing of the second instruction. So the cycle is just the same as it was for the first machine code instruction. We do a fetch of the instruction from main memory, we do a decode, and then we execute. So you can see when we examine slide 41 that the 5 steps that we executed for the first instruction when we fetched it, they're identical to the 5 steps that we'll execute just now for fetching this machine code instruction. The only difference is the value of the PC register, which was 50 when we did the first instruction and which is now going to be 51. So without any further delay, what I'll do is I will take you through frame by frame the fetching of the machine code instruction stod 101. So step number 1, we take the value that's in the PC register 51, which is the address of the cell which is to be fetched, decoded and executed. We copy that into the memory address register. That's the first step, and then we have the control unit assert to the circuitry of the main memory a read operation. The circuitry of the main memory sees that it has to interact with cell 51. It sees that the operation that's required to be executed is a read, and then what it does is it basically goes into cell 51 and it copies the content of cell 51 so that it is output over the memory bus and becomes an input to the CPU. The CPU then reads the value that's on the data lines of the memory bus, which is stod 101, and it brings it inside the CPU, and now that value stod 101 is stored inside the memory buffer register. And then from the memory buffer register in step number 4, we copy the value of the memory buffer register through the ALU, and we bring it up into the instruction register. Now the value that was in the instruction register previously, which was the machine code instruction loco 10, that's now gone, and it has been overwritten by the new machine code instruction which is to be executed, which is stod 101. The next step is to increment the PC register by 1 so that it points to the address, the memory cell address of the next instruction which will be executed, which is loco 13, but we'll get to that in a moment. So that's the fetch. The fetch part of each instruction, as I said, is always the same, except with the difference that the PC register will be obviously a new value for each new machine code instruction. Okay, so now we decode it. So if we look at the table of machine code instructions and you look at stod, you'll see that stod is an abbreviation from store direct. And if you look then at the column that says actions, you'll see that when that machine code instruction is executed, the value of the accumulator will be copied to the memory address specified by X. So in this case, the memory address that we'll be copying into is 101. Now you'll remember, if you go back to the beginning of the presentation, that we said that the 3 variables A, B and C, that they were associated with specific memory locations. So when we look at the computer, you can see that the instructions, they occupy the range of addresses from 50 through to 60, and you can see that above them there are three cells, memory address 100, 101 and 102. Well, they're reserved for the values that will be assigned into the variables A, B and C. So we'll see that in a second. So essentially what will happen is that the value that is in the accumulator, which is the value 10, will be copied out to the cell 101, which is the cell that's reserved for the variable A. Okay, so we'll go through that. There's three components to that. So what the control unit does is it looks at the machine code instruction that is in the instruction register. It splits it into two components, the operator, which is store direct, stod, and the operand, which is 101. So 101 doesn't mean the value 101, it means of course the address 101. Okay, so what the control unit then does is it takes that value 101 and it sends it down to the memory address register, and then it goes to the accumulator and it takes the value that's in the accumulator, which is the constant value 10, and it copies that through the network of buses to the MBR. Now you might say to yourself, well, why does it go through the ALU? Well, remember that the network of buses inside the CPU is unidirectional, so there is only one route that can be taken by the value 10 as it travels from the accumulator to the MBR, and that is through the A bus and then down through the ALU without any change and then into the MBR. Once the two memory registers have been set up with the address that is to be written to and the data that is to be sent to the address in main memory, the next thing that the control unit does is it sends a write signal to the circuitry of the main memory, and it also sends the value 10 out over the memory bus, where it is then read by the circuitry of the main memory, and you can see that the value 10 gets copied from the memory bus and into the cell whose address is 101. Now the net effect of that is, after having executed two machine code instructions, loco 10 and stod 101, that what we've actually done is equivalent to the high level instruction A is equal to 10. So remember, 10 was our constant value that we brought inside the CPU and put in the accumulator, and then we had to get that 10 and bring it from the accumulator out to the memory cell that was set aside for the variable A. So at this point we've done, after having executed two machine code instructions, well, we've observed the control unit and the CPU having done 16 distinct operations to basically carry out something that we would have thought was very straightforward, which is making A equal to 10. So we're going to look now at the execution of the third instruction. So I would expect that at this point we can start to speed things up a little bit, because essentially what we're doing is we are executing machine code instructions that we've already seen, except with slightly different values. So you can see that the third instruction is local load constant 13, and that it's stored at address 52, and basically we can see that we have to fetch local 13 from address 52, decode it and then execute it. So as you saw previously for the first two instructions, the fetch part of the cycle, which takes 5 separate operations, is essentially the same as the previous fetch operations. The only difference is that the value that will be the memory address that we'll be fetching from will be address 52. So we can step through this. We can see that the value that's in the PC register 52 gets copied from the PC register to the memory address register. You can see that illustrated there. The control unit of the computer then asserts a read losing control of the diagram there. Then asserts a read operation. So you can see that the read command gets sent to the circuitry of the main memory. The circuitry of the main memory does two things. It reads the value that's in the memory address register, which is 52, and it sees that its instruction is to read. So it goes to cell 52 and gets the contents of cell 52, loco 13, and copies them out so that they get sent over the memory bus and they become an input to the CPU. The next thing that happens is that the CPU reads the inputs from the data lines of the memory bus, and the loco 13 is brought inside the CPU and temporarily stored inside the memory buffer register. Step number 4, as before, is for the contents of the memory buffer register to be copied through the data path, through the ALU, up through the CBus, and then into the instruction register. The previously stored machine code instruction, which was stod 101, it gets overwritten by loco 13, and then the final thing that the control unit does as part of the fetch is to increment the PC register from 52 to 53 so that it now points to the address of the next machine code instruction. So that's the fetch part. Now we look at the decode part. For this instruction, loco 13, and being mindful as well that we have a table in front of us which tells us what each of the instructions does, we can see that loco stands for load constant, and we can see by looking at the actions column where the effect of the machine code instruction is specified in terms of transfers from the registers. You can see that the effect of this instruction when we execute it is that a constant value C, which is the 13, will be copied into the accumulator. So this is very similar to the first instruction, and in fact if I step through it frame by frame, you can see that what the control unit does is it looks at the machine code instruction in the instruction register, it splits it into two parts, the operator, which is loco, and that says okay, and the control unit then says alright, I know what I have to do here, and then it looks at the operand, which is 13, and it copies the operand out of the instruction register and brings it down as an input to the ALU, and then from the ALU it copies it unchanged via the CBus up so that it becomes an input to the scratchpad register, and then finally step number 3, it copies the value of 13 from the CBus and puts it into the accumulator. So you can see that the value 13, which obviously is going to end up being stored in the variable B, that is now stored inside the accumulator, and that is the end of the Fetch-Decode-Execute cycle for the third machine code instruction, which is called loco 13. So instruction number 4 is stod 102, and you can see that its location in main memory is in memory address 53, and as before, and this is getting a wee bit predictable I think at this point, the instruction has to be first of all fetched, and then it has to be decoded, and then it has to be executed. So as before, you can see that the 5 steps in the fetch are the same as they were for the first 3 instructions, and you can see that the only thing that's different is the value of the memory cell, the address of the memory cell that we will be fetching from. So stepping through it, we can see that the first part of the fetch is to take the value that's in the PC register, the program counter, and copy it into the memory address register. So value 53 ends up inside the memory address register. The next step is that the control unit of the CPU sends a read instruction, a read command to the main memory. Main memory reads the address, which is 53, reads the read instruction and says okay, I have to copy the contents of cell 53 to the CPU. So that's what it does. It reads the contents of cell 53 and sends the contents of cell 53 as data over the memory bus, so that that becomes then input to the CPU. The CPU reads the data lines of the memory bus and it copies into the memory buffer register the machine code instruction stod 102. And then finally, or penultimately, what happens is that the contents of the memory buffer register are copied from the memory buffer register via the data path, via the ALU, and brought into the instruction register. The newly arrived machine code instruction stod 102 overwrites the previously stored machine code instruction, which was loco 13. So that is now overwritten. And that, once we've incremented the PC register by 1, so it goes from 53 to 54, which is the next address of the next machine code instruction that will be executed. That is the fetch part of the fourth instruction. So the decode part is to store the value that's in the accumulator into the memory address 102. So again, when you're thinking about what a machine code instruction does, hopefully you'll always have the printed table in front of you, and when I look up the second row of that table, I can see that stod_x stands for store direct, and when I look at the actions part of that table, you can see that whatever values in the accumulator gets copied into the memory address x. Okay, so in this particular instance, x is 102, and we can see that what's going to happen is that the value 13, which was put into the accumulator by the third machine code instruction, it's going to end up being copied into cell 102, memory cell 102. And remind yourself that all our variables A, B and C, they are stored in separate cells. So B is stored in memory address 102. So let's step through what the control unit would do. So remember that the machine code instruction stod 102 has two parts to it. Stod is the operator and 102 is the operand. So the control unit examines the first part, the operator, and says, okay, this is a store direct operation. And then it looks at the operand, and because it knows the type of machine code instruction that has to be executed, it takes the operand part and it copies it to the memory address register. It then takes the value that's in the accumulator and it copies it through the network of internal CPU buses, the data path, to the memory buffer register. And then the next step that the control unit carries out is to send a write instruction to the circuitry of the main memory, and the circuitry of the main memory says, okay, I have to read the contents of the memory buffer register, which is 13, and I have to copy those that value into the memory address 102. So you can see the animation shows the 13 traveling away from the memory buffer register, being copied over the memory bus, and then ending up being stored into cell 102. So the upshot of all of that is that when we've executed the machine code instruction store direct stod 102, well, that coupled with loco 13 is essentially equivalent to the high-level programming instruction b equals 13. So at this point, with 4 instructions executed, we've actually initialized 2 variables a and b with the values 10 and 13 respectively. So we're now on the 5th instruction, and you can see that the 5th and the 6th instructions are very similar to the 1st and the 2nd instructions, and then the 3rd and the 4th instructions. So it's the same thing, and this is the great beauty of it. Although it's quite complex, it's just the same thing repeated over and over and over again. So our 5th instruction is loco 0, and that lives at instruction or memory address 54. and when we fetch that instruction, it's the same 5 steps as before, with the only value being different being the value of the cell that we're going to interact with, which is memory address 54. So basically we can step through the animation. It should be getting familiar to us at this point. So we're fetching loco 0 from memory address 54. So the 54 gets copied from the CPU to the memory address register like so. We then have the control unit of the CPU assert a read instruction to the circuitry of the main memory. The circuitry of the main memory reads the memory address register, reads the value that's contained therein, which is 54, and then the circuitry goes to cell 54 and gets the contents of cell 54 and causes the contents of that cell to be copied out over the memory bus so that it becomes an input to the CPU. The CPU then reads the data lines of the memory bus and copies the machine code instruction into the memory buffer register, and then the next step is for the contents of the memory buffer register to be copied up through the data path and brought into the instruction register like so. And then the fifth and final part of the fetch is for the PC register to be incremented by 1. So now it points to the next address in the sequence of machine code instructions to be executed, which is the machine code instruction that is at cell address or memory address 55. So we've now fetched the instruction loco 0 into the CPU, and our next step is to decode it. So again, if we consult our table, you can see that loco is an abbreviation for load constant, and if you look at the actions column, you'll see that the effect of executing the machine code instruction loco is that whatever your constant value is gets copied into the accumulator. So we've seen this already twice before, and we can very, very quickly step through it. So the control unit looks at the machine code instruction that's contained inside the instruction register, splits it into 2 parts, the operator and the operand, sees that the operator is loco, and then says, okay, I have to carry out the following implementation steps, operations, the first of which is to copy 0 through the ALU and then into the accumulator. So you can see that the value 0 goes to the ALU, and then from the ALU it becomes an input to the scratchpad registers, and then finally it ends up being copied into the accumulator where it overwrites the value that was there previously, which was 13. So that's the machine code instruction loco 0, now fetched, decoded and executed, and we'll now proceed to the 6th machine code instruction, which is stod 100. Okay, so our 6th instruction is stod 100, and it's stored at memory address 55. And as before, we can see, well, there is the fetch part. So at this point, fetch is becoming, I think, very, very familiar. 5 steps to each fetch. Only thing that differs from the previous examples of the fetch is the value of the PC register, which in this occasion will be 55. And again, we can quickly step through the animation. 55 gets copied from the PC register into the memory address register. The control unit then sends a signal to the circuitry of the main memory, which is read. The circuitry of the main memory reads the value that's in the memory address register, which is 55, and says, okay, I've been told to go to cell 55, read the contents of that cell and copy them out over the memory bus. So you can see there's the contents of cell 55 travelling towards the CPU, and then the CPU opens up its data pins and it copies the machine code instruction stod 100 into the memory buffer register. And then the next step is to take the contents of the memory buffer register which contains the machine code instruction, and arrange for it to be transmitted through the data path so that the machine code instruction gets copied from the MBR to the instruction register. Whatever value was previously stored there gets overwritten, and then our fifth step is pretty simple and pretty straightforward. The PC register has to be incremented by 1, so now it points to the cell of the next machine code instruction that will be executed. So that's the fetch part of the machine code instruction stod 100 done, and now what we'll do is we'll look at the decoding and executing of that machine code instruction. So we've seen this machine code instruction stod before, and again, go back to your table of available machine code instructions and you look up stod.x, and you can see that stod is an abbreviation for store direct. And then if you look at the actions, you'll see that it shows you that whatever value is in the accumulator ACC register gets copied from the accumulator register and sent to the memory address X. Now in this case, X is 100. So all that's going to happen is that when we decode and execute store direct 100, what will actually happen is that the value that's in the accumulator, which is 0, the consequence of the last machine code instruction, which was loco 0, well, what will happen is that that value 0 will get copied into the memory address 100. So you can see that as before, the control unit of the CPU looks at the machine code instruction that's inside the instruction register, breaks it into two components, the operator, which is stod, and then on the basis of its examination of the operator, it then carries out the necessary steps to actually execute the instruction. So the first part of that is to take the operand, which is 100, copy it into the memory address register, and then take the value of the accumulator, put that into the memory buffer register, and then send a signal to the circuitry of the main memory, which is that the main memory will be performing a write, which it duly does. So you can see that the value that's in the memory buffer register, which is 0, is copied over the memory buffer register, over the memory bus, and becomes an input into the main memory circuitry, and then eventually it ends up in the address 100, which has been specified in the memory address register. That effectively, at this point, after we have executed loco 0 followed then by stod 100, that's effectively equivalent to the high level statement C equals 0. So at this point, we've actually executed 6 of our 11 machine code instructions, and if we go back all the way to a table that we looked at very early on, you'll see that this table tried to capture, if you like, the meaning of the entire program, all 11 machine code instructions. So you can see that effectively what we've done is we've executed these first 6 machine code instructions, which had a binary form, and effectively all we've done with those 6 machine code instructions is we have initialized those variables A, B and C with their respective values of 10, 13 and 0. So the next 2 instructions that we'll be executing will be related to the addition of A and B, and then the 9th instruction, which will be a stod instruction, will be the assignment of the sum of A and B to C, and then the final 2 instructions will be our output to the terminal. So we'll look at that in the next segment of this lecture. So now we'll be looking at the 7th and the 8th instructions of our program. So the 2 instructions, although they're treated separately because they're both the object of separate Fetch-Decode-Execute cycles, we can think of them as being grouped together because essentially what is done with the 7th and the 8th instruction is we add together the two variables A and B. Okay, so I'll step through the 7th instruction and the 8th instruction, and then we'll see how those two instructions together actually implement A plus B. So the 7th instruction, like all the instructions that we've looked at so far, starts off with our fetch. So recall that the fetch is the same for every single machine code instruction. The only difference that applies is that the PC register is different for each of the fetches. So we're now on the 7th instruction. We started at instruction that was stored at memory address 50, and now we're at the 7th instruction, which is stored at memory address 56. So it's the same deal as before when we consider the fetch. We start off with the value that's in the PC register being copied through the data path and being asserted into the memory address register. When that's been done, the control unit then asserts a read instruction to the circuitry of the primary memory. The primary memory then reads the value that's inside the memory address register. It accepts the read instruction, and it then carries out the operation that it's been instructed to carry out by the control unit, and it goes to memory cell 56, and it looks inside memory cell 56, and it copies the contents of memory cell 56 over the memory bus so that it becomes an input to the CPU on the data lines of the memory bus. The next thing that happens, of course, is that the CPU reads the data lines of the memory bus, copying whatever values are being asserted there into the memory buffer register. And then the next step is to transfer the machine code instruction that has been read from primary memory via the data path into the instruction register of the CPU. And then finally, as ever, we increment the PC register by 1. So the PC register now contains the value 57, which is the memory address of the next instruction that will be executed when this instruction has been fully decoded and executed. So once we have done the fetch part, it's then time to actually go ahead and decode and execute lodd 101. So lodd 101, and again I'm consulting my table, which I have printed out in front of me, and which you should have in front of you when you do this exercise. So this is slide 23, and basically if I look at the table and I look up lodd, I'll see that lodd is abbreviation for load direct, and if I look up the actions column, I can see that the consequence of fetching, decoding and executing lodd is that whatever value is stored in the specified memory address X will then be copied into the accumulator. So we can see just by looking at the slide that the memory address that is going to be copied into the accumulator when lodd 101 is executed is of course memory address 101. Now if you cast your mind back, you'll remember that memory address 101 was set aside to store the value of the variable A. So effectively what's going to happen is we're going to take the value of A, which we had previously initialized to 10, and we're going to copy it from the main memory into the CPU, and specifically then into the accumulator register. So we go ahead and we step through the various instructions or little operations that are needed to do that. So this is the control unit that takes responsibility for this, and we can go through it step by step. So the first thing that the control unit would do is it would examine the machine code instruction stored inside the instruction register. It would split it into two parts, the operator and the operand. It would look at the operator. It would recognize the bit pattern for lodd, which is 0000 according to the table that I have in front of me. And it would say, okay, I have to execute a sequence of steps in order to carry out a lodd instruction. So the first of those steps is to copy the operand part, instruction IR, instruction register operand, to the MAR, to the memory address register, to then assert a read command to the circuitry of the main memory, which then, after a delay, responds and goes to memory cell 101 and gets the value that is stored in memory cell 101 and copies it out of the main memory and as a set of signals which are then transferred as an input to the CPU. The next step is for the CPU to read the inputs that's being inserted at the data part of the bus, bring it into the MBR, and then from the MBR transfer the value 10 through the network of internal buses inside the CPU, the data path, so that they become an input to the scratch registers and then become a value inserted into the accumulator. So that's the 7th machine code instruction executed, and effectively when we have fetch, decoded and executed that, the effect of executing that is to take the value 10 from main memory where it's stored in cell 101 and bring it into the accumulator. So now we proceed to execute the 8th instruction, which is the machine code instruction add 102, which is stored at address M57. So this is quite a complex instruction. It's probably more complex than anything that we've looked at so far, but as ever it begins with a fetch of the instruction from main memory. So this is the same 5 steps that we've seen already executed 7 times previously, and you can see that it begins with the value that is in the PC register, which in this point is 57. So we can see that the PC register value 57 is copied via the data path to the memory address register. Then the control unit asserts a read signal to the circuitry of the main memory. The circuitry of the main memory responds by looking at the value that's in the memory address register. It sees that it has to attend to memory cell 57, and because the instruction that has come from the control unit of the CPU is read, that means then that the contents of cell 57 have to be copied from that cell and sent to the CPU via the memory bus. And you can see there's the data travelling over the memory bus towards the CPU. The next thing that happens, of course, is that the CPU reads the data from the data lines of the memory bus and copies the information that's been presented there into the memory buffer register, and then that is in turn copied from the memory buffer register to the scratch pad registers and specifically into the instruction register, where it will be subsequently decoded and executed. And then finally we see that the PC register itself is incremented from 57 to 58, so that means that the next machine code instruction that will be executed will be the one that's stored at cell address 58, and that will be done when we are finished with this machine code instruction. Okay, so that's the fetching of the 8th machine code instruction. Now let's consider what that machine code instruction actually does when it's decoded and executed. So what I'm going to do is I'm going to consult my table of machine code instructions, slide 23, which I have printed out in front of me. And we can see that when the machine code instruction add x is executed, that this is, in terms of what it does, known as add direct. And if we look at the actions column, we can see that the register transfer notation specified there tells us that whatever value is in the accumulator is added to whatever value is specified, or stored inside the memory address inside the memory cell with the address x. So we know that the accumulator has the value 10 stored in it from the execution of the previous machine code instruction. Recall to mind that 10 is the value that was assigned to the variable a, and we know that b had assigned to it a memory cell which had the address 102, So basically what we're going to do is we're going to go out to main memory, we're going to go to memory cell 102, we're going to retrieve 13 from that memory cell, bring it into the CPU, add it to the value that's in the accumulator, which will give us a sum of 23, and then we'll store that 23 into the accumulator, overwriting the value that was previously there. So let's step through that. You can see that there are 6 steps that we have to process, and we start off with the control unit looking at the machine code instruction that's stored in the instruction register, splitting it into 2 components, the operator, which is add, and then the operand. So by examining the operator, the control unit can see, okay, I have to carry out the predetermined, pre-specified steps that will actually add the accumulator and the specified memory address. So we can see that the first thing that the control unit does is it takes the 102, which is a cell address, and it copies it into the memory address register. The second thing that the control unit then does is it asserts a read instruction to the main memory, and we can see that what happens is that the circuitry of the main memory goes to cell 102. It gets the value that is contained inside memory cell 102, which is 13, and it copies that value out of the main memory and sends it towards the CPU via the memory bus. You can see that the next thing that happens is that the CPU reads that value of 13 from the memory bus into the memory buffer register, and then it asserts it as an input to the ALU. At the same time that the value 13, which of course is the value of B, is being asserted as an input into the ALU, the control unit also arranges for the value of the accumulator, which is 10, which I'm sure you'll remember is the value of the variable A, to also be asserted as an input to the ALU. So remember that the ALU had 2 inputs when we studied it previously. It had an A input and it had a B input. So we can see that the 2 numbers that are being asserted here as inputs to the ALU are 13 and 10. The next step is for the control unit to send a signal to the ALU, and that signal is add. Now if we could zoom in on the ALU control lines, we would see that the signal that would be being sent would be 1-1 if we were being consistent with the circuit that we studied previously, and I think for the sake of convenience we will say that. So the ALU then responds to that, it's enabled, and the inputs 13 and 10 are passed into the ALU, and we can imagine that those 2 inputs are sent to parallel adders where they are added together, and then the ALU, once it has done the addition of 13 and 10 inputs A and B, copies the output, which is 23, onto the C bus. So then the next step after that is to take that 23 and to send it up to the scratch pad registers and to copy it into the accumulator. So you can see now that the accumulator has accumulated the sum of 13 and 10. So remember that 10 was originally stored in the accumulator, and that the 13, it came from memory address 102. So that is the execution of the 8th machine code instruction, which has added 2 numbers together, and then the sum of which has then been stored into the accumulator. So now we're going to execute the machine code instruction, the 9th machine code instruction of this program, which is stod, store direct 100, which is located at address M58. So as before, we have to fetch the instruction into main memory before we decode and execute it. So it's the same 5-step sequence that we've seen before, and of course the only difference is that we're looking at the PC register value of 58. So just quickly stepping through the animation part of the fetch, you can see that the value of the PC register is copied from the PC register to the memory address register. The control unit asserts a read to the circuitry of the main memory, and then after a period of time the circuitry of the main memory interacts with cell 58, and it causes the contents of cell 58 to be copied from the cell and out onto the memory bus, where it becomes an input to the CPU. CPU reads that input from the memory bus and takes the copy of the machine code instruction into the memory buffer register, and thence from the memory buffer register to the instruction register, where it will then stay when it is being decoded and executed. And as ever, the fifth and last part of the fetch is to increment the PC register by 1. So now the PC register is equal to 59, which is obviously the address of the next instruction that will be executed in the sequence of instructions that make up our high-level program. So now that we have done the fetching of stod 100 from address 58, the question is, what does this instruction specifically do? Well, again, I go back to my table of machine code instructions from slide 23, which is printed out in front of me, and I look up the entry, the row for stod X. Stod stands for store direct, and when I look at the action column, I can see that the effect of this machine code instruction when it is fetched, decoded and executed is that the value that is in the accumulator will be copied from the accumulator to the specified memory address X, which in this case has the value of 100. So this is effectively the equivalent of us assigning the value 23, which resulted from the addition of 10 and 13, which are the values of A and B. Remember that that addition took place with the last machine code instruction that was fetched, decoded and executed. That was the add machine code instruction. Well, once we had done the addition, you'll remember that the value 23, it ended up in the accumulator, and we did remark that the next thing to do would be to assign the value 23 from the accumulator into the memory address that was associated with the variable C. So we know that the variable C is associated with memory cell 100. So there are 3 steps to this, and in fact we've seen this instruction I think 3 times before when we were initializing the variables at the beginning of the program. So it's pretty straightforward. As before, the control unit examines the machine code instruction that's inside the instruction register. It looks at the operator, which is stod, store direct, and on the basis of that examination of the operator, it determines that it has to do a sequence of specific steps in order to carry out the store direct operation. So the first of those steps is to take the operand, which is 100, the memory address 100, copy it to the memory address register. The second step is to assert it's not to assert, it's to copy the value of the accumulator into the memory buffer register. So we have our address specified, and we have the bit of data that's going to be sent to that specified address, and then we assert, the control unit asserts a write signal to the main memory, and the value 23 is read from the memory buffer register, communicated via the memory bus to the main memory, and then the circuitry of the main memory, having read the memory address register and seen that it is cell 100, then takes the value 23 and it writes 23 into the memory cell with the address 100. Now when it does that, the 23 overwrites the value that was there previously, and the value that was there previously was 0, and that was the value that we gave 0 when we set up the program, when we set up the variables of the program, and we gave each of the variables an initial value. So C was initially set to 0, but now as a result of the addition, it now has the value 23. And that concludes the execution of the 9th machine code instruction, which is the assignment of 23 to the value C. And that's described in the caption of this particular slide. So now we head to the last two instructions, which are pretty straightforward. So remember that what we did in the high level version of the program was we had three variables, A which was equal to 10, B which was equal to 13, and then we added the two together to give us 23, which was assigned into a variable C, which had initially started with the value of 0, but which when we had done the addition took the value 23. So you'll remember that the final line of that high level program was print C, and that's what the 10th and 11th instructions do. So I'm very quickly going to go through these because actually they are pretty straightforward. So the 10th instruction is lodd 100, which is at address M59, and when we execute that, you'll see that it is, as before, fetch, the 5 steps that we've done so many times already in regard of the fetch, except this time the PC value is 59. So you can see that step by step we take the value of the PC register, we copy it to the memory address register, the control unit then asserts a read instruction to the main memory. The main memory responds by going to cell 59, which is the address that's specified in the MAR register, looking at the contents of that cell and then copying them from cell 59 onto the memory bus and then transferring that data to the CPU. Once it's been asserted as an input to the CPU reads the machine code instruction into the MBR, and then from the MBR it transfers it directly to the instruction register via the data path. And then, as ever, we increment the value of the PC register from 59 to 60. So the PC is now equal to 60. So having fetched the machine code instruction lodd 100, we now go ahead and we execute it, and we've seen this instruction several times before, but basically what we're going to do is execute lodd 100 load direct, and again, if we consult our table of machine code instructions, you can see that the effect of that is that the value that's specified by the operand, which is a memory address, is copied to the accumulator. So the net effect of this when the machine code instruction is executed is that the contents of memory cell 100 will be copied into the accumulator, remembering of course that the cell 100, the memory cell 100, that was the cell that was specifically set aside to store the contents of the variable C. So we go ahead and we'll go through that. Slightly complicated set of operations to do the decode and the execute, but as ever it always starts off with the control unit examining the machine code instruction inside the instruction register, looking at the operand and the operator. The operator is lodd, so that tells the control unit what it has to do, and then the first thing that is done by the control unit is to take the operand 100 and send it to the memory address register. Once that value has been asserted into the memory address register, the next step is for the control unit to say to the main memory, read. The circuitry of the main memory responds by going to cell 100, the cell that's specified in the memory address register, and it looks at the contents of that cell and it causes the contents of that cell to be copied out and sent to the CPU via the memory bus. 23 is then asserted as an input to the CPU, and the CPU copies that value from the memory bus and puts it into the memory buffer register. Finally, that value is copied via the ALU, via the data path, and is asserted as an input into the accumulator, and then finally you can see that the accumulator takes the value 23. Now you might be saying to yourself, why would you load a value in from main memory which is already present in the accumulator? So you can see that we overwrote 23 with the value 23. Now the reason why we're doing that is a teaching point that relates to the behaviour of machine code instructions when we look at slightly more complex structures in programs. So one thing I would just draw your attention to is that the high-level program that we've looked at is entirely sequential in nature. But you know from your studies in Java that programs can also have conditional structures and iterative structures. So conditional structures are things like if statements, and iterative structures are things like while loops and for loops. So it turns out that it's always best, especially when we're thinking about these more advanced type of programming constructs, iteration and selection, conditional selection, to actually explicitly load the value in, even though there's a possibility it may already be present. It's a safer thing to do, and you will see that when we get to the assembly programming part of the course. But in any case, we have now fetched, decoded and executed lodd 100, and we now only have one machine code instruction left to execute, and that's what we'll attend to next. Okay, so our final instruction is a pretend machine code instruction, which I've labelled as out. It's the last of our machine code instructions that make up our simple program. It's stored at address 60, and basically it has the same fetch phase as the other 10 machine code instructions that we've looked at. So our PC register value now is 60, and we go through the same sequence of steps that we've done before. So PC value 60 gets copied to the memory address register. The control unit tells the main memory, read. The circuitry of the main memory goes to the cell 60 that's specified in the memory address register. It gets the contents of that cell and it copies it to the CPU. CPU then reads the data bus, the memory bus, and copies the machine code instruction from the data bus into the MBR, and then finally it takes it into the instruction register. Now step number 5 here shows the PC register being incremented to the memory address 61. Now at this point we've finished our example, and I haven't specified what machine code instruction would be present in cell 61. It's quite possible that we would have a machine code instruction like halt, which would terminate the program, or it might be that our program continues on. But in any case, we don't care, because I think at this point we've demonstrated in pretty decent detail the fetching and decoding of 11 machine code instructions. We don't need to do a 12th and a 13th instruction. Okay, so that's the fetch part of it, and then when we look at the decoding and executing phase, rather than getting into a lot of gruesome detail about printing out and so on and so forth, all I've said is that the way that the out machine code instruction works is that the value that is in the accumulator is sent to an output device where it can then be displayed. So you can see here that I've pretended that there is a terminal device, a little bit like our Linux screens or our DOS screen, and there you can see the 23 that was in the accumulator being printed out to the outside world as output that can then be read by a human. So that's the last of the instructions, and what we'll do next is we'll think about maybe some of the things that we've learnt from stepping through this animation of the Fetch-Decode-Execute cycle. Okay, so we've finished executing our program, and hopefully what this animation has done is given you a reasonably decent insight into the execution of the Fetch-Decode-Execute cycle. So I think an idea that we should have in our heads, that one of the objectives of this course has been to try and explain the working of the computer from the ground up. So at this point, if things have gone to plan, then hopefully you've got a reasonably decent idea of how a program like the one that you might write would in principle be executed at the different levels by the computer system. But I think we can also make a few other specific remarks. So my initial comments, and I think these are things that you will have observed as we proceeded through the animations. Our first point is that the fetch part of the cycle is always the same sequence of actions, with the exception of the PC value. So we saw that over and over and over again, and we can see that it becomes actually quite familiar to us. So even though when you initially looked at this video, when I probably did it in class, you were probably quite intimidated by what was the apparent detail and complexity. What you should be able to see is that these instructions, they're quite primitive, they're quite elementary, but the important point about them is that they are very, very specified, they're very predictable, they're all hardwired in to the circuitry of the CPU. So we note that, and then I guess the other thing that we should note is that the specific effect of each instruction when it's decoded and executed can be described in terms of this register transfer notation. So I make a fairly big deal about this because this register transfer notation is what we'll have to keep in mind when we go to do the assembly programming exercises over the next couple of weeks. And then I guess the other thing that's important is that when we did this manually, it was very tiresome, I suppose, but the CPU, because it's a machine, because it's an electrical machine, can really execute many of these instructions very, very quickly. So I don't know what the actual figures would be for a contemporary CPU, but I would expect that we could do millions, tens of millions, hundreds of millions of these instructions in a second. And as we saw, the individual instructions, the individual machine code instructions, very, very, very primitive, but that doesn't really matter because if you can execute 200 or 300 million of them in a second, you can do a lot with those primitive instructions. The second last slide is really just about the machine code that we'll need to familiarize ourselves. So we'll be seeing this table again in some detail. I referred to it all the way through this demonstration, and you'll certainly need to look at it again when we go to do the assembly programming. But the important column is really this column here, which is the specification of the effect of each machine code instruction when it's been executed, and that's quite important. Now, to come to the things that you should be able to do, well, you should certainly, and this is without exception, be able to name the significant components of the data path. So these are all the bits that are inside the CPU. You should be able to describe, name and describe the ALU, the three different scratchpad registers, the instruction register, the program counter register, and the accumulator register. You should be able to name and describe the purpose of the two memory registers, which are the memory address register and the memory buffer register. You should certainly be able to describe their function. You should certainly be able to describe the 5 basic features of primary memory, which are that they are an array of memory cells, that the cells have contents which are either instructions or data, that each cell has a memory address, and that the main memory can support read and write operations on individual cells. And ideally, and this is number 4, you should be able to give a description of the steps executed at each stage of the Fetch-Decode-Execute cycle. And I think that we'll be talking about that later, but even if you're not able to do a verbatim description, which admittedly would be a big ask, I think and I hope that you've had some reasonably decent insight into the Fetch-Decode-Execute cycle, such that if somebody says to you in the future, well, what is the Fetch-Decode-Execute cycle, you would at least be able to offer a rough summary of what we've discussed today.